残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
Okay, what's up everybody? We're back to working with some derivatives. We're talking today about maxima and minima. Now, this is one of the most important parts of calculus. This is why we even really bother to study the derivative. So, now that we know a little bit about it, looking at some of the information contained in the derivative, we will be able to get information about the maximum and minimum values of a function on a given interval. So, this does have some real-world significance. For example, many functions' values represent practical quantities, such as the profits of a company, the surface area of a container, speed of a space vehicle, and a million other contrived examples. So, let's get on to the first definition. Definition 1. Absolute maxima and minima. Let's let f be defined on a set D containing a point C. If f of c is greater than or equal to f of x for every x in D, then f of c is an absolute maximum value of f on D. If f of c is less than or equal to f of x for every x in D, then f of c is an absolute minimum value of f on D. An absolute extreme value is just one of these two, either an absolute maximum or an absolute minimum. So, an important thing to notice here is that the existence and location of absolute extreme values depends both on the function and the interval of interest. Let's look at an example to get a sense of what's going on. Okay, so if we want to get an idea of what's going on with maximum and minimum values, what's going on with extreme values, let's look at a couple of classic examples. First off, let's look at a basic parabola. We can notice that right here at the vertex of the parabola, if I vary a point around it, notice everything is higher than that point. I.e., this is the lowest point on the graph of the function right there, yeah? This is as low as it goes. Okay, fair enough. Similarly, if I flipped around to a parabola opening downwards, I could see that the vertex is the highest point on that parabola. That's as high as it goes. It is higher than everything nearby, and indeed, higher than everything on the whole function. Okay, cool, easy enough. Now, there are other things that happen. So, looking back at these two examples, notice the derivative is 0 at the maximum value here, and the derivative is 0 at the minimum value right here. But if I switch to another example, maybe try something like a cubic, you can see that at the top of this little hill and the bottom of this little valley, you definitely have 0 derivatives as well. Now, something to notice here, basically, this looks like a little chunk of one of the previous examples. It's like that parabola opening down, right? This little guy, that little chunk right here, not so different in a big way. I.e., if I zoomed in pretty close on this little chunk right here, I would be pretty close to looking at what's going on over here. It'd be a little bit different, but basically the same behavior is going on, but only on a small piece. The same thing is going on this side. On this side, I basically have the parabola opening upwards, a little bit different, but, just on a small piece. So notice, this is not the lowest point on the graph of the function. I have lower points over here, and this is not the highest point on the graph of this function. I have higher points over here. But nearby, this is the highest point, and nearby, this is the lowest point. This motivates the idea of a local minimum or a local maximum, as opposed to, say, a global or absolute minimum and a global or absolute maximum. Okay, so let's define a local maximum minimum value. So let's suppose that C is an interior point of some interval I on which f is defined. So let's take a quick second and think about interior points. What does this mean? Oh, let's get a better line than that. So if I grab a line right here, and here, let me get to a different color, make things a little bit easier. Let's say we're going from a point A, so let's make this a closed interval, over to a point B. So I'm drawing this with like the brackets, like, like how you write A, B, like that. Oh, lost the tail of that guy. There you go. So I'm writing this the same way, i.e. I'm keeping those endpoints, yeah? So there's something to notice here. Let's switch to a different color and check it out. All right, if I pick a point in here between A and B, i.e. in this interval, in this guy right there, notice if I take any open interval around this guy, make basically like a little ball, yeah? All of those points in that ball there, on that line, are inside the interval as well. If I choose something over here, same business. And in fact, even if I get extremely close to the endpoints, I can still do this. But if I go to one of the endpoints itself, half of it's in there, but the other half isn't. So this is what an interior point is. Basically, it's just not the endpoints or points that are just by themselves. So idea is that if you can't fit a little open interval around your point inside of the bigger interval, then that point is not an interior point. i.e. if you can pick a point, draw an open interval around it, and everything in there is in the big interval, then that point is an interior point. All right, so with the idea of an interior point out of the way, pretty intuitive, just really not an endpoint. Let's get back to the idea of a local minimum and a local maximum. So if f of c is greater than or equal to f of x for every x in the interval, then f of c is a local maximum value of f. And if f of c is less than or equal to f of x for every x in I, then f of c is a local minimum value. i.e. if we jump back to the graphs, let's check those bad boys out. All right, back here, notice I'm going to flip this one back on. There we go. Over here, notice that if I choose a interval around -1, or whatever that top point is, some interval around here, then tracing up, this guy is a maximum on that interval. Similarly, over here, this guy's a minimum on this interval. Now, if I draw the interval too big and get something, say, over here, then this guy stops being the minimum. Oops. This guy stops being the minimum if I pick up points over here. Similarly, this guy stops being the maximum if I pick up points over in this area. So it's saying that on some smaller interval, these guys are maximums and minimums on that interval. i.e. the difference here is just where you're looking. Basically, the gist of it is that you can be the tallest person in your house without being the tallest person in the world. i.e. local maximums and minimums versus global maximums and minimums, and that's the whole idea. Okay, now let's talk a little bit about the first theorem of the section, the extreme value theorem. So, basically it says that a function that's continuous on a closed interval, here let's just call it the closed interval from a to b, has an absolute maximum value and an absolute minimum value on that interval. This is actually a lot more straightforward than it first looks. So let's draw ourselves a picture quick. Oops. Basically, the gist of it is, if I give myself a little bit of a y-axis here, grab myself a bit of an x-axis, and then I'm going to switch colors. All right, let's mark down an A, and let's mark down a B, and let's just draw any function that I can do without picking up my pen. Yeah? Something like this. How about it? Okay. Switch colors just make things a little bit easier to see. Naturally, I can trace up to right here, trace on over, get f of a, go over here, trace on up, get a f of b. All right, and notice that between here and here, there is a highest and lowest value, i.e. if I draw a line starting from someplace and going to someplace and I don't pick up my pen, no matter how I draw it, whether I did it like this guy or here, let's change colors and do another example. If it's a different function, maybe instead I'm going, up through here and then I fly the heck off and I go way down and I go way up and then I just go do this or something. Who even cares? Notice, still, between here and here on this closed interval, because I drew this without picking up my pen, there is a highest point right up there, and there's a lowest point right down there. Same business with the pink curve. If I start at a place and I end at a place, and I don't pick up my pen, doesn't matter how high I go, I have to get back down to that point. Doesn't matter how low I go, I have to get back up to that point. So, basically, what it says, if you look here, we're just tracing over. Basically what it says, and this is actually really cool to think about, what this is telling us is that continuous functions send closed intervals, i.e. here to here, to closed intervals. Takes this guy, spits out that guy. Having a highest and lowest value means that it's gonna be a closed interval. Now, how do we know that we get all the points in between? Well, if we didn't, we'd have to do a little bit of a jump. This is a consequence of the intermediate value theorem, which we talked about earlier. So extreme value theorem plus the intermediate value theorem tells you that continuous functions send closed intervals to closed intervals. Kind of neat. All right, it's kind of nice. There's also a local version of the extreme value theorem. Basically, this guy says that if f has a local maximum or minimum value at a point C, and that's the important bit there, and f prime of C exists, then f prime of C is equal to 0. Notice it's totally possible to have a local max or a local min without f prime of C existing. Here's a quick example. So, absolute value functions kind of look like V's. You could shift them, move them around, all that sort of stuff, but if you have a function in some way given by an absolute value, it's going to look something like that, yeah? Okay. Notice now, if I pick up, say, let's pick an interval. I don't know, it doesn't even matter. Let's take A to B, just like that. Who knows what A and B are? It doesn't matter. Picking up something down here, going over here, picking up something over there. Okay, so the highest point is right at that peak. But at that peak, as I'm approaching from one side, my tangent line is just, it's just that line. And as I go from the other side, my tangent line is just this line. It's all of the reasons we looked at before, that there is no derivative here. But all the same, this is as high as it goes. And this over here is as low as it goes. So, local maximum or minimums occur where you have derivatives, precisely at places where you have a zero derivative. But it's also possible to not have a derivative and have a local max or a local min. Now there's a tiny little piece here we should be careful on. We're adopting the convention here that local maxes and mins only occur at interior points. So this is a absolute minimum on the interval from A to B, but it is not a local minimum because it occurs at an endpoint, which, as we talked about before, is not an interior point. This guy, however, is an interior point, i.e. if I take that point, I can grab an open interval around it that's fully contained in that interval from A to B. So that is a local maximum, and it's at a place where the derivative doesn't exist. But whenever the derivative does exist, then it's got to be zero. Let's look back at our graphs real quick to see exactly how this works. All right, let's tab on over. There we go. Looking at this guy, local maximum. Hey, wouldn't you know it, we definitely have a zero derivative right there. Down here, local minimum, wouldn't you know it, zero derivative. Doesn't matter if you look at the parabolas, these are absolute maximums and minimums, but still, a zero derivative. Oh, a zero derivative, yeah? Basically, the gist of it, if we want to sketch ourselves a quick little tangent line here, let's do a quick bit of deriving. All right, so I'm just taking the derivative, I'm putting a in there for the moment, x minus a, and then I'm just going to add on to that the value of the function there. Sorry, this is a little bit of a messy guy here. A to the third minus 2a plus 1. And I'll add a slider there for a. All right, now I've got something that traces out. Oops, almost. Did I screw something up? Let's see. Am I getting the right thing? Oh, minus 2. There we go. All right, cool. Wrote down the wrong thing. Perfect. So now I've got something tracing out my tangent line as I go. Notice it's got positive slope over here, and as we get close to that top, I get to that 0 at some place, just right around -1. I flip from being positive slope to negative slope, and then over here I flip from negative slope to positive slope, i.e. the tangent lines are telling us when we change direction, and the zeros of the derivative, the places where the tangent line is horizontal, those tell us precisely where we end up switching directions from either increasing to decreasing or decreasing to increasing. Now, there's a big question. Is the converse to this true? The answer is no. So let's stop right here real quick and just do another function. Let's do x to the third. If you look at x to the third now, we can pretty clearly see that at 0, we're going to get out a tangent line of 0. If we want to throw in a slider for that, 2b to the second, let's see, x minus b plus b to the third. I'll add a slider for b. Now I can see that, so let's go from -1 on over to 1. Step 0.01. Bam. Okay. So now I'm just varying this tangent line across here, and oh, wouldn't you know it, you got a 0 at 0. Yeah? But that's not a max or a min. Not local, not global. So sometimes, and this is where the slight distinctions are that I think maybe make this a bit tricky for folks. Sometimes you can have points where you have 0 derivatives that are not maximums or minimums of a local or global variety, but when you do have a derivative and you do have a local maximum or minimum, then that derivative has to be 0. However, in the other direction, not having a derivative does not mean that you don't have a maximum or a minimum there. So there's a little bit of nuance here. We'll do some examples to get used to this. Before we get to any examples, though, let's take one last definition that will make our lives a lot easier throughout this process. So we'll group together all of these different cases in one very nice way. We'll define a critical point. So an interior point, let's call it C, of the domain of a function, let's call it f, at which f prime of c is equal to 0, or where f prime of c fails to exist, is called a critical point of f. I.e., these are interior points where f prime of c is 0, or f prime of c is not defined. These are, by the previous examples we just looked at, potential spots where you could have local maxima or local minima. I.e., these are the places where you could go higher than any nearby point or lower than any nearby point. All right, so with this language in hand, let's get on to examples. Okay, on to the first example. Example 1. Find the critical points of f of x equals x squared times the natural log of x. First step, we'll find our derivative. So f prime of x, using a little bit of the old product rule, will be 2x times the natural log of x plus x squared times the derivative of natural log of x, which is just 1 over x. Doing a little bit of algebraic manipulation, we can turn this into 2x times the natural log of x plus x. And to finish things off, I'm just going to write this as x times 2 natural log of x plus 1, i.e. I'm going to factor an x out of both terms. So from here, the next thing I should do is I should set my derivative equal to 0 and solve for that. So f prime of x is equal to 0. Well, that's equivalent to saying x times 2 natural log of x plus 1 is equal to 0. So be careful here. At first, this might seem to say that x could be 0. I.e., if you plug in x, it looks like this will be 0. Except for the fact that natural log of x is not defined when x is equal to 0. So this tells us that the derivative is not defined when x is 0. Does that make 0 a critical point of f of x? No, because a critical point is either a place where the derivative is 0 or where the derivative is undefined, and a point which is in the domain of the function. So the derivative is undefined or 0 at a point in the domain of the function. That's the definition of a critical point. This point, x equals 0, is not in the domain of natural log of x, so it's not in the domain of f of x. It doesn't matter that the derivative is undefined, it's not in the domain in the first place. So our only option is that 2 times the natural log of x plus 1 has to equal 0. All right, let's solve this. So this tells us that 2 ln x has to be equal to negative 1. Dividing by 2, this would tell us that the natural log of x has to be equal to negative 1/2. Since e to the x is the inverse function of natural log of x, this says that x is equal to e to the negative 1/2, which, if you want, you could rewrite as 1 over the square root of e. And hey, there you go. You've got your final answer. That is the only critical point of f of x. Perfect. So we'll get on to more examples in just a moment here, but let's talk about our strategy for determining local maxima and local minima, and absolute maximums and absolute minimums. So we know that theorem 1 guarantees the existence of absolute extreme values of a continuous function on a closed interval from a to b, but it doesn't say where these values are located. That is, the extreme value theorem tells us that every continuous function has an absolute maximum and an absolute minimum on any closed interval. To determine where they are, we're going to use the following procedure. So, assuming the function f is continuous in the closed interval a to b, which, side note, doesn't mean that you can just assume this for any function, but assuming that you have a function that is continuous, then this is what we'll do. 1. We'll locate the critical points c in the interval from a to b. That is, where f prime of c is equal to 0, or where f prime of c does not exist. These points are candidates for the absolute maxima and minima. 2. We'll evaluate f at these critical points and at the endpoints of the interval. 3. We'll choose the largest and smallest values of f from step 2 for the absolute maximum and minimum values respectively, i.e. we'll find all the places where we could have a max or a min, and then we'll check and see which one's the biggest and the smallest. This will tell us which one actually is the max and which one actually is the min. Okay, let's do one. Okay, on to an example. So, example 2. Find the absolute maximum and minimum values of f of x equals x to the fourth minus 2x to the third on the closed interval from minus 2 to 2. So, I've already written the answer here to save us some time. I'll show calculations and steps along the way. Because f is a polynomial, we know that its derivative exists everywhere. After all, its derivative will be just another polynomial. So, if f has critical points, if it has any of them at all, they are points at which f prime of x is equal to 0, since a critical point is a place where the derivative does not exist or is equal to 0. So, these are the only places where it can happen. Computing f prime and setting it equal to 0, we have that f prime of x is equal to 4x to the third minus 6x squared. This is just a consequence of the good old-fashioned power rule. Naturally, we can factor out a 2x squared from both of these terms, giving us 2x squared times the quantity 2x minus 3. Naturally, if we set the derivative equal to 0, that's the same as setting this equal to 0. There are two solutions to this. One when x is equal to 0. Another one when x is equal to 3 over 2. Okay, this gives us two critical points. Both of these lie in the interval from minus 2 to 2. Be careful, this is an important step to check. If you find critical points that aren't in the interval you're looking at, you're just wasting your time if you evaluate them. Okay, so these are candidates for the location of absolute extrema, i.e. absolute maximums or absolute minimums. If we evaluate f at each of these points, we see the following. F of negative 2 is 32, f of 0 is 0, f of 3 over 2 is minus 27 over 16, and f of 2 is 0. Now, I'm not going to show exactly how to go do all these. We have calculators. Just plug it on in. It's pretty easy to see that the largest of these values is f of negative 2, which is 32. This tells us that 32 is an absolute maximum value of f on the closed interval from minus 2 to 2. The smallest of these values is f of 3 over 2, which is equal to minus 27 over 16. This tells us that minus 27 over 16 is an absolute minimum of f on negative 2 to 2. If you want to look at a graph of this function, you can see that the critical point x equals 0 corresponds to neither a local maximum nor a local minimum. And in fact, if you want, we can check that out pretty quick here. Here you have exactly that function we were looking at the last example, x to the fourth minus 2x to the third. Notice you do have a minimum right down here, and at 0 you have neither a maximum nor a minimum. Let's plot some vertical lines to see exactly what's going on. Oops. Let's see. X equals minus 2 and x equals 2. These vertical lines are showing us that in this little interval, we have, wow, it gets pretty tall. Okay, as you can see, at negative 2, way the heck up here, we get 32. That's hard to fit in the picture. If we zoom in a little bit closer, we can see that at 2, we get another point, but it's neither a max nor a min. The lowest point occurs at 1.5, i.e. 3 over 2. So our answer is correct, and 0 is indeed neither a maximum nor a minimum. On to the next example. Here, we'll find the absolute maximum and minimum values of the function g of x equals x to the 2/3 times the quantity 2 minus x, and we're doing this on the interval from -1 to 2, including the endpoints. So, once again, I've written out the example to save us some time. I'll highlight details with handwritten calculations. Differentiating g of x, which, notice, if we expand it, makes things a little bit easier, since x to the 2/3 times 2 minus x can be rewritten as 2 times x to the 2/3 minus x to the 5/3. What we get is that g prime of x is equal to 4/3 x to the minus 1/3 minus 5/3 x to the 2/3. Now, notice, because we have a negative in this exponent right here, g prime of 0 is undefined. 0 is in the domain of g. I can certainly plug 0 into g, and 0 is in the interval from -1 to 2. So, x equals 0 is a critical point of g. In addition, g prime of x is equal to 0 when 4 minus 5x equals 0. Let's highlight that calculation. So, just notice that g prime of x is equal to, as we have right up there, 4/3 x to the minus 1/3 minus 5/3 x to the 2/3. Now, let's factor out a 1/3 x to the minus 1/3, i.e. 1/3 times x to the minus 1/3. All right, this just leaves us with 4 minus 5, and when I take x to the 2/3 divided by x to the negative 1/3, that's the same as taking x to the 2/3 times x to the 1/3, which is just x. There we go. So now we can see that 4 minus 5x equals 0 tells us that g prime of x is equal to 0. So x equals 4/5 is also a critical point. Notice, 4/5 is less than 1 and bigger than 0. It's in the interval from -1 to 2, for sure. These two critical points that we found, x equals 0 and x equals 4/5, as well as the endpoints, are candidates for the location of absolute extrema. The next step we do is just evaluating g at all the critical points and endpoints. G of -1 is 3, g of 0 is 0, g of 4/5 is approximately 1.03, and g of 2 is equal to 0. The largest of these values is g of -1, which is 3. So, 3 is an absolute maximum value of g on the closed interval from -1 to 2. The smallest value we get is 0, and this occurs twice. This isn't a problem. While the smallest value happens at two different places, it is still the unique smallest value. Okay, so g has an absolute minimum value on the closed interval from -1 to 2 at the critical point x equals 0 and the endpoint x equals 2. This absolute minimum value is 0. There we go, another example down. Real quick, let's look at a graph of this function. So, jumping into a graph here, I've already plotted the function as well as the two lines that bound our interval. So between here and here, it's pretty easy to see that we have our biggest point, our highest point in that graph, at -1. Similarly, we have our two lowest points at 0 and at 2, and both of those have values of 0. So our work is right. We calculated this without even ever knowing what the graph of the function looked like. Pretty cool. Okay, let's do one final example, this time with a little bit of a real-world vibe. So, example 4. A stone is launched vertically upward from a bridge 80 feet above the ground at a speed of 64 feet per second. its height above the ground t seconds after launch is given by f of t equals negative 16t squared plus 64t plus 80, and this is valid for times between 0 and 5 seconds. When does the stone reach its maximum height? So let's sketch ourselves a quick little picture. Alright, I'm going to do some axes right here just to make our lives a bit easier. Now I'm going to switch colors to keep everything readable. Okay, so we've got ourselves some kind of a bridge about 80 feet up. And here we've got some guy standing, and he throws a little stone. So it starts at the height of 80 feet, right there. 80 feet, yeah? And it goes up to some highest point, and then it comes down and hits the ground. So let's find out when the stone reaches its maximum height. To begin, we must evaluate the height function at the critical points and at the endpoints of our interval. The critical points must satisfy the equation f prime of t equals 0. Since f is just a polynomial, this is a pretty straightforward derivative. F prime of t is just negative 32t plus 64, which follows immediately using the power rule. So, factoring out a negative 32, this just becomes f prime of t equals negative 32 times the quantity t minus 2. Setting this equal to 0, we can pretty easily see that the only critical point is t equals 2. We now evaluate f at the endpoints and at the critical point. So, f of 0 is 80, which is exactly what we expected. F of 2 is 144. This picture is not exactly to scale. So that's 144 feet. And at 5 seconds, we hit the ground. So, on the interval from 0 to 5, including the endpoints, the absolute maximum of the height function occurs at t equals 2, at which time the stone reaches a height of 144 feet. Because f prime of t is the velocity of the stone, there's an interesting additional interpretation here. The maximum height of the stone occurs at the instant the velocity is 0. I.e., you've probably seen this if you've ever thrown a ball in the air. That moment where it just hangs there, right at the top. That's its highest point. And there we go. Done with the last example.
Omedetou. めでたいな。おめでとさん。